Where do we have questions? We take a look at our breakdown. First week's done, second week's done, third week. What are we, the seventh? Fourth. Ah, we're only the fourth. Um, so you should have actually watched the Lewis and Vesper one, which is a long one, but that covers all the kind of primary content behind Lewis structure. It does have a section in it, if you've not watched it, where it's like you no longer need to continue watching this because that's not relevant for our class. If you're interested in watching it, you can do so, but realize that content is literally not relevant for Chem 130. Okay. Um, the ionic Lewis structure, the next lecture in this is really just practice. So it goes through a couple different Lewis structure things and tries to get you to kind of think about how to put it together. And that is ultimately the end of our content for this unit. Okay. So what we'd be left with is the ability to pretty much do any question within the practice exam. Okay, it would be fair game. Or we could double through some practice on Lewis structure, because I would argue you probably need practice with Lewis structure. Yeah? Okay. So from the vigorous head shaking, yes, I'm going to say that we're going to look at Lewis structure first. And then if people have other questions, we can kind of adjust. This is a giant wall of text, and I kind of apologize for that. But this outlines all of the steps that you should go through and do. Okay, these steps should look familiar because they're taken from the slides. Okay, and they should also be familiar if you've gone to the tutoring center, because the tutoring center has a worksheet on Lewis structure. Their worksheet in the past was absolutely god awful, and I hated it with an unadulterated passion. For whatever reason, they listened to me, and I told them they need to adjust. And so the rule set that they now have in the tutoring center on their worksheet is this. Okay, it is the same approach. Okay, realize we do have some shifts at the bottom of this, because again, this rule set is supposed to apply to multiple classes. Okay, Chem 130 pretty much stops at rule 7, and you just assign formal charges to the molecule. You just use brackets and you say, but that's what it is, and we don't worry about it. As you go through more advanced chemistry classes, you start to get more and more specific about where things go, and that's where the rules have those extra things behind it. Okay, so critical steps that you need to be paying attention to as you go through and process this. We do want to total our valence electrons. Okay, we ended Monday, okay, looking at electron configurations, and so you could use the electron configuration. The highest number, any energy shell that is in that number counts as a valence electron, and you would then total that. Okay, as we talked about, that can be a bit tedious and obnoxious to deal with, so we said there was a shortcut. What was the shortcut? What was that? Yep. Yeah, just look at the column number. Okay, so up there at the top on this one, it says 16 or VIA. The A is actually a label for that section, so that's not dealing with Roman numerals. So it's really 16 or VI. What is VI in Roman numerals? 6. Okay, what is 16 minus 10? Why are we minusing 10? It's not the first two shells. It's the D block. You're just sectioning those out, okay? Because those have been assigned numbers, okay? We don't care about those numbers because when we talk about Lewis structure, as far as y'all are concerned, we're only care about octets, which is a term we'll deal with, but octets should sound familiar because you got the root oct in reference to 8, like octopus, okay? Or octagon if you have a different perspective. So all you've got to do is look at that column number, and that tells you your valence electrons, okay, for any element within it. So if we look at PO for, do we know that one?
Plutonium?
Nope, it's PU. PO is polonium, okay, with 84 electrons, has the exact same number of valence electrons as oxygen does with only 8 electrons total. Okay, because you're looking at the outer energy shell. We don't care about anything on the interior. Okay, So that can simplify our counting process. We don't have to deal with electron configurations. We just have to recognize how to total. Okay, so you'll total all your valence electrons. You do have to account for charges. I'll try and pick some examples that don't have charges first. You choose a central atom. That central atom needs to be the least electronegative. Problem with electronegativity is it's not really defined within your textbook. Okay, so the other definition you can use has to do with metallic character. Okay, the most electronegative is the least metallic. Which element is the most metallic? Yeah. Okay, so if you've got electronegativity memorized, I highly encourage you to maintain that and stick with that. Ignore the metallic conversation we're about to have. Your metals are on the left-hand side of the periodic table, so the further left you are, the more metallic you are. Okay? The lower you are, the further away from the non-metals you are. So the lower left corner is your most metallic. Okay? Your least metallic would be the upper right. Okay? When we're dealing with Lewis structure and electronegativity and even metallicity to a certain extent, we ignore the noble gases. What are the noble gases? That's the far right column. We ignore those. Why do we ignore those? What's that? Flip it. Yeah, they're insanely stable. When we're talking about Lewis structures, we're talking about how atoms react with each other to form some kind of connection, a chemical bond. The noble gases don't form chemical bonds, so you don't have to worry about them for the most part when dealing with Lewis structure. For this class, absolutely, we won't do them. If you move into 151, sometimes you'll see instructors talk about them.
Is it because they have octet already?
So cool. Why? Why would they be elements that don't react? Well, if you go through and process them and look at their electron configurations, what are you going to find? For all of their orbitals, they are max filled with electrons. Okay? Since they're max filled, they don't need anything. They're happy where they're at. Okay? That's the reason behind that. And you can push that to octets. It goes a step beyond octets, but it's a decent first approximation.
Can they bond with other atoms?
Yes. Okay. So one of the things that you've probably experienced in most of your science classes is we say, oh, there's this rule. And 5 exceptions to that rule. Okay. For the most part, there aren't rules. They're patterns that we've seen. So when we talk about the noble gases, the general pattern is they don't form bonds. Okay. Can I make them form bonds? Yeah. Okay. Rich people, sorry if you're rich, tend to hoard money. That's why they're rich, right? Can I make them give up their money? People are like, no way. I'm pretty sure I can. It's called war. Okay. I can make rich people give up money. That's absolutely fair game. Just like noble gases, I can make the noble gases make bonds. Okay, so we can force it, but what you're doing isn't shifting your realm into those edge cases of those parameters. Okay, so our central atom needs to be the least electronegative. Okay, and then the rest of your atoms will scatter around that central atom. Okay, future classes, you lose a central atom. Nothing is central. Okay, right now you have a center atom, put your center atoms around that, or put your other atoms around the center. Okay, where should you place them? You should place them on the faces of a square. Why a square? Okay. Origins of Lewis structure and how he went through and thought through this was he was looking at sets of 8 and he said, what shape has 8 corners? A cube. We don't want to draw a cube, so we squished it and turned it into a square when we're drawing in 2 dimensions. Okay. You then go through adding electrons in pairs to the most electronegative. I see your hand. Give me just a second to finish this thought. Okay. When it comes to this rule is probably the most challenged rule out there. Most instructors do not use this rule and try a bunch of other hand-wavy BS. Let's be nice. Okay. That, quite frankly, is designed so that they don't have to explain what's happening on the bonding system. Okay, and why? Because they failed OCHEM. Okay, I absolutely 100%, and I failed OChem too, for the record. Okay, so you really have to understand what's going on with your structures to be able to manipulate these things. And when it comes to Lewis structure, it's kind of a one-off topic. You get a lot of instructors that didn't like structure, and so they come up with any way that they can teach the content to avoid the content. Okay, and that holds true for everybody. Okay, so you want to add your electrons in pairs to the most electronegative atom. Okay, electronegativity is a big thing. You need to manipulate that. Okay? Yes.
So in the lecture examples, we had to break down sulfur and 3 oxygen algorithm structure for that. And you had mentioned like there's specific ways to write them. You know, you can't just move them around. So my question is the correct way when you have 3 of them, you have sulfur in the middle. You have 2 on each side? Is it top or bottom? Like, does it matter?
Okay. So right away you could say, well, you had 2 on each side. You could go top or bottom. Who said it had to be 2 on each side? Couldn't it have been top and bottom? And then which way do I do? Left or right? Okay. So the exact location on those faces ultimately doesn't matter. Once you've picked an orientation, that orientation of where you've placed things needs to stay constant. Okay. And that needs to stay constant for rule 6, which is probably the most challenging of these.
Okay. So I was
Okay.
assuming like resonance kind of fixes some of that issue. You have to write all the different ways.
It fixes and it complicates. Yeah. So once you've picked your orientation, that's the orientation you're locked in. Okay. But we have to realize that, well, since you opened it, let's talk real quickly about that. Is it that button? Yeah. Okay. If we did sulfur, oxygen, oxygen, oxygen versus sulfur, oxygen, oxygen, oxygen. Okay. Again, once we've picked it, we're locked into that orientation. Okay. But let's say we haven't picked it yet. Which one of those correctly represents this? Okay, and this is the hard question. Yeah, absolutely both. Okay, why?
Instance where you would have to write out all of the possible.
This isn't even resonance, because we haven't even gotten to that. We haven't said anything about electrons. Resonance is electrons. What we're talking about is where do we place those atoms on the faces of a square, which I didn't draw the square, but we can draw that, of our center atom. So structure A, we place them on left top bottom, left top right, sorry. And on the structure B, we went bottom left top. Okay, does it matter? Okay, well at this stage, it doesn't matter. I can place them wherever we want. And the reason for this has to do with what we're trying to represent with this. What are we trying to represent? Yeah, the molecule. Well, where is that molecule? Which is also an equally hard question. Ah, is it on the paper? Our drawing is on the paper, but where is the molecule? The molecule is in our 3-dimensional world. What we're trying to represent is the 2-dimensional aspect of that 3-dimensional object. Okay? And so the analogy that I would use a lot when dealing with this kind of orientation, kind of system, would be like straightforward, real quickly, pop quiz, everybody ready? What's my name? Cool. What's it now? Still Mike. All that happened is you just turned it a little bit. That's okay. Okay? That's the first time someone laughed that much. I feel a little bit happy. Yeah. Okay? But that's all that's happening, is you're just looking at it from a different orientation. Okay? And since this one's more of a bend, I didn't do the full turnaround because that one also creates interesting name calling. Okay? So once you've picked your configuration, you're now locked and you need to maintain that configuration. But until you've picked it, you can do anything you want as long as it's dealing with those faces. Okay? Does that kind of make sense? Why aren't you doing what I asked? Thank you. Okay. Then once you've placed your electrons around your most electronegative, you then go through and continue to add electrons into your structure until you've achieved the total electrons. This is why step 1 is so flippin' critical. Because step 1 tells you how many electrons you're allowed to put in there. Okay? So you'll continue to place them. Once they're all placed, you can now have this conversation. And again, this is one that people don't like doing, but I would argue is relevant to break it down into this step. Anywhere you have a pair of electrons between atoms, you turn into a line connecting the atoms. Why? I'm saying that's a chemical bond. And I want to differentiate the bond from not bonds. Okay? So we can use the notation to help us understand that and see that. Depending on who you talk to, particularly it seems like it's old or foreign chemists at this point, okay, you'll see them turn every pair of electrons into a line. I disagree with that philosophically, okay, but it's not wrong. It changes how you interpret and where you see things. Okay?
How do you know if the pair of electrons are bonded or not bonded?
Let's go back to our sulfur. I didn't need to draw all that detail out, but I did already. So we would place electrons around our most electronegative first. Okay, I place it around our oxygen up to the octet. Okay, so there's 8 electrons around it. I then go around my next oxygen, and I could do my next oxygen. Sulfur has 6, oxygen has 6. There's 3 of them. This gets me 24, right?
18.
Plus the 6. Okay, so 24 total. I apologize, I didn't do that math right. So I have 24 electrons now drawn in this. How do I know I have a bond or not a bond? Well, the bond is a line. When do I draw a line? When do I draw a line? We just did this. We just did this. We did the rule. What's the rule? When do I draw a line? It's not because I have a bond. No. When do I draw a line? How do I know the electrons are being shared? They're between 2 atoms. That's it. So when I go through and I look at this, see this pair of electrons? Is that pair of electrons between the oxygen and the sulfur? So what should I do? Turn that into a line. How do I know that that is now a bond and that these 2 electrons are not a bond? Well, is there another atom there? Nope. So I'm not going to convert that into a line yet. Okay? And the other one I know is a bond because I drew it as a line instead of the dots. This is why I like to differentiate those to help with this. It can be a bit obnoxious because you'll note, particularly as I drew it, you're trying to draw dots. So you can try and make darker dots so you actually see them. Random pencil strikes can look like dots. So you do have to be a little bit careful with that. Does that help? Okay. Then you'd hit rule 6. Okay. Rule 6 is the tricky one. Okay. But in rule 6, what you're now going to do is move pairs of electrons to ensure that all your atoms have their octet. Okay. And it notes there is a quote there for quotes their octet. Okay. Do all atoms need 8 electrons? No. What atom does not need 8 electrons? Hydrogen's pretty much going to be the only one you'll see, though officially we could look at boron and aluminum. Even then, there are scenarios where you would go through and show them achieving 8 electrons. So hydrogen doesn't have an octet because it caps out at 2. So you'll sometimes hear reference to hydrogen having what rule? Octet was 8. Hydrogen doesn't have 8 electrons, it only has 2. And if 2 people sang together, you'd have a duet. So you'll sometimes hear it referenced as a duet rule. I think that's dumb. You're creating a rule for a single atom. Just acknowledge that it can only hold 2. Okay? When it comes to moving those non-bonding pairs, if there was more than one pair that you could have moved, okay, or rather more than one atom nearby that had non-bonding pairs, you're now moving into the realm of dealing with resonance. Okay? And if you encounter that scenario, You're now responsible for acknowledging all those possible conclusions, which means, yes, drawing multiple structures. Okay, kinda, sorta. Okay, we just talked through the rules. We didn't really apply them yet. You're trying to rely on whatever you saw from the lectures and then sneak that back into this. We're going to try and play around with some examples. Let's try it. Clear everything. Dude, whenever I want to use my hand, it doesn't let me. And every time I don't want to use my hand, it does let me. So just like in the tutoring center, okay, you've got an example that kind of breaks this down. This one I left some blanks on it to kind of help you kind of guide through. So you could go through and set this up as a 5-step system, arguably 6-step, we'll worry about that later, okay, for each of your structures. What you'll find is most people, as I already started to do, draw on top of the same structure, okay? Whatever helps you get to the answer correctly is fine. You don't have to box this out. Okay, so if we were going to look at methane, CH4, I have a carbon and 4 hydrogens. Step 1, I need my valence electrons. Carbon has 4 valence electrons, and I know that because on the periodic table, its column name is 14 or Roman numeral 4. Hydrogen has 1, but there's 4 hydrogen atoms, so I have to multiply that by 4 times. Okay, 4 and 4 gets me 8. Step 2, I picked my center atom. Okay, which one's less electronegative, carbon or hydrogen? Hydrogen! But I didn't put hydrogen in the middle. One of the caveats on that rule is that center atom must be able to bridge. Okay, so that means it has to be able to do 2 bonds. 2 bonds means how many electrons? 2 bonds, each line is a pair of electrons, which means 4 electrons. How many electrons can hydrogen have around it? 2. Hydrogen can never bridge. So hydrogen will never be the center atom. So electronegativity is ultimately a trend that you would memorize. Okay, fluorine is the most, and then you'll typically see people call cesium the least. It's a little bit more complicated than that. That's not going to steer you wrong. So I think that could steer you wrong. Don't do that. Okay. What you would memorize is fluorine is the most, and then cesium is the least. You're like, well, isn't francium lower? Yes, francium is lower. Why do we not memorize francium? Okay. Francium, see the little parentheses underneath it for the atomic mass? Why? Man-made, insanely unstable. Because it's so unstable, does it exist for long enough to us to make a compound? No, which means there's no point in evaluating its electronegativity. Okay, it's a purely thought experiment. So when we talk about electronegativities, our trend, fluorine most, cesium least. Okay, I don't have a periodic table up here, but right, close enough, periodic table. Okay, you could go through and draw an arrow and you could say electronegativity. Okay, when would you do something like that? When during the exam? Love that answer, that was fantastic. At the very beginning of the exam, because odds are you'll remember the electronegativity at the beginning of the exam, but 20 questions in, you're going to forget it and screw it up. So put that information, brain vomit the stuff that you're memorizing down onto paper so you don't have to hold on to it anymore, and then always reference back to it.
So the central atom is picked on first whether or not it can bridge, and then if it can, it's either electronegativity.
It's electronegativity, yeah. So your central atom should be the least electronegative. That can bridge. Okay? So step 2 is identified. What was step 3 and 4? Add our electrons. So if we go back to our system, our carbon, our hydrogen, I'm going to redraw it. there's my box. I guess I should do a different color for my box. And now I want to add electrons. Where do I want to add the electrons? And I'm going to get nitpicky with this answer. Where do I want to add the electrons? I don't want to add them in bonds, which is what I think you were suggesting. You're not wrong, but again, I'm really trying to nitpick the detail of what you're doing, not the final answer. Face of the square. Starting with the face of the square is okay, but should I start placing them around the hydrogen or the carbon? Okay, so we're getting a couple different answers, which is a bit obnoxious because I'm misleading you, and I would argue no. Where else can I place them if not on the carbon or the hydrogen? It's how you're phrasing it. Where do I need to place the electrons? What was the rule? What? But where do I start placing them? What was the rule? It was just up there. How could you possibly have forgotten? There it is. It's the most electronegative element. That's where you need to start placing your electrons. That's your focus. Why not? Well, carbon was most electronegative. Can I place them there? Well, if I change the compound to CO3 and you start placing them around the carbon, you're now placing them in the wrong space because they go around the oxygen. Okay? So when we're thinking of our process, the words that we use have power. And if you start saying, I want to place them on the carbon, you're going to start changing that into, I want to place them on the central atom. Okay? I always want to put them on a carbon. Well, what if there's no carbon? Okay? That's not the process. The process is the most electronegative. Since carbon is the most electronegative, I want to start placing them around the carbon first. Okay? And I'm going to place them on the faces of the square. That's why I drew the square out, because it can help me with that. Okay? In that placement, I do also want to start, which somebody suggested over here, that might have been you, okay, that I want to place them in between where atoms are already located. Why? If this is a molecule, I know I need a bond there eventually. I might as well start placing electrons where I know I need to have them. Okay? So I could place a pair of electrons there. I can place a pair of electrons there. I can place a pair of electrons there, a pair of electrons there. How many electrons have I placed? 8. Now that I have 8 electrons, I could now move on to step 5. And step 5 was, I think, anywhere I have a pair of electrons between atoms, I can turn into a bond. So there's my box again. I guess, again, the box should be a different color than my letters. So there's my hydrogen, 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 hydrogen. Did I have a pair of electrons on the left face of the box? Yes. So line. Top face. Right and bottom. Okay. Now I need to go through and check octets. Does every atom have 8 electrons around it? Okay, cool. So we're getting a good answer there because I asked the question. Okay. No, not every atom has 8 electrons around it. Did every atom need 8 electrons around it? No. Okay, good. The hydrogen only needed 2. How many electrons are around each hydrogen? 2. The hydrogen, that line represents 2 electrons, and the hydrogen has access to them. How many electrons are around the carbon? 8. Okay. You will sometimes hear, and I hear it coming from tutors, and again, it's probably from tutors being trained in Gen Chem wrong. Okay. They start going through and count out the number of valence electrons. There are no more valence electrons. They are gone. Valence electrons happen in step 1. The placement of all my other electrons is now, where do I place the molecule's electrons? Okay. Every line I've got is a pair of electrons. As long as that line touches my atom, I can count that pair of electrons to that atom. Kind of, sort of? Okay. The other thing I want you to be aware of in this approach, there were no Legos. Okay. You'll sometimes see people going through, I tried to zoom in and it didn't. It's good. That was nice. Okay. Let's draw out a pet peeve. Okay. Carbon has 4 valence electrons, so I'm going to draw 4 electrons. Hydrogen comes in and has, did someone just gasp? Because hopefully it was a yawn. Hydrogen has 1 valence electron. Hydrogen has 1 electron. 1 electron. Oh, and now I can just snap them together and I have a motherfucking structure. That atoms are not fucking Legos. Okay? That is a bullshit approach. which is why those particular people that teach that method suck at OChem, because they don't understand the balance of where the electrons are going. Okay? Draw out the process here, and it works. When does it work? This is the beauty of it. All the time. When does this Lego thing work? It only works in the small subset of sections that don't have any real chemistry associated with them. Okay? That was a cop-out so that they didn't have to teach proper chemistry. Okay? And I totally understand that, for the record. Sometimes we have to do cop-outs to navigate. I get it. Okay? But stop doing that cop-out. Okay? Yes?
Real quick, so if there was any atom other than hydrogen, then those would also have to have 8 electrons.
Yes. Yep. Okay? So when we consider the resonance, all of our atoms have octets. I don't need to move any electrons, which is good because I don't have any electrons to move. The electrons I'm allowed to move are the non-bonding electrons, and I got none. Right? So do I have to worry about resonance? Nope. Don't have to worry about it at all. That's now my final structure. Okay, do I have to worry about formal charge? Was this molecule charged? Where do I see charge? In the top right-hand corner. Okay, of our structure, we drew that. How did we get to the structure? Where did step 5 come from? Step 3, 4. Where did step 3, 4 come from? Step 2. Where did step 2 come from? Where did step 1 come from? That's an eraser. That came from that formula. Is our compound charged? Where do we see charge? In the upper right-hand corner. What do you see in the upper right-hand corner? Nothing, which means no charge. Since there's no charge, there's no need to show brackets, and I'm done. Okay, that's the end formally of Lewis structure. Okay, after Lewis structure, we point out that Lewis structure has its flaws, because if we look at that molecule in the actual reality of the world, okay, it doesn't look like that. Because if we look at that, it looks like all the hydrogens are on a flat plane, right? Okay, well, each of those groups of electrons are negatively charged, right? And so when I see one line see the other line, what are they going to do? They're going to push away from each other. Okay? Since all of those lines are equivalent, they're all connected to carbon and hydrogen, they all need to push equally far away from each other. Did they all push equally far away from each other? Okay? And this is going to come from how you're looking at the patterns. Some people might go like, yeah, totally, it's 90 and 90 and 90 and 90. So they're all pushed perfectly away from each other. Cool. What about these two? That's 180. These aren't pushed equally away from each other, which means this does not accurately reflect our physical reality. It reflects a two-dimensional representation, and if we wanted to scale this up to the three-dimensional reality, we would have to then go through and do a couple potential things. You could play around with model kits. Some people bring in marshmallows. You could take marshmallows and stab toothpicks into it to represent your bonds and say, where can I put those marshmallows or the toothpicks so they're so far away from each other? I never liked that demonstration because the marshmallows were always too soft and the toothpicks always moved wherever the hell they wanted. Okay, so instead what I do is just go through and try and define your systems. Okay, you'll talk about, it says electron regions. So we'd go around that square and we say, where do I have electrons? Do I have electrons on this face? This face? This face? This face? Okay, doesn't say anything about how many, just are there electrons on that face? And as long as there's electrons on that face, that counts as an electron region. I have 4 regions of electrons. Because I have 4 regions of electrons, I now need to memorize the shape that comes out of it. I don't want to memorize. Then get yourself some marshmallows and some toothpicks and start figuring out those shapes. Even then, you're going to be like, oh yeah, this totally looks like this shape. But that's not the shape that somebody else decided to call it that you're responsible for. Okay? What is the shape? It's right there. You're just holding up your hand. No, I'm not holding up just my hand. Okay, right in the middle, okay, kind of my knuckles, that's the carbon. What is this finger? No. That's the bond. The tip of my finger would be the hydrogen, 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 and then what's my wrist? The wrist is the hydrogen, the carbon's the knuckle in between. Sorry, I can't get 4 fingers to pull this shape off. Okay? And that's my tetrahedral shape. Okay, that's the name of it. I call it tetrahedral. Okay? It turns out that as we draw out more complicated structures, we'll get systems where those bonds are not all equivalent. Because they're not all equivalent, are they all going to spread out to be the exact shape? No, they tweak. And because they tweak, they get a new shape. Which then means you're responsible for knowing that shape. Okay? And that's that Vesper giant ugly table that comes out of it where it talks about the electron regions, and then it talks about bonding versus non-bonding. Okay? So for this particular structure, we have 4 bonding regions, which means it's electron geometry. I'm not talking about bonds now, just electrons is tetrahedral. I would then evaluate bonding versus non-bonding. I have 4 bonding regions, which then means it's also tetrahedral. So the electron geometry and the molecular geometry can sometimes be the same thing. Okay? So just like all instructors are wont to do, we pick the simplest example, and then what do? Really? Nobody has an idea? Okay, since you have no idea, I'll educate you. Then we'll go ahead and we will move to a hard example. Do sulfur dioxide. Okay? Some of it is started for you. You actually have some answers already identified on this. But go through and attempt sulfur dioxide on your own with the people around you. If you have questions, please raise your hand. I'll help kind of guide you through each of these steps. A couple minutes maybe, and then we'll draw it all out together. And then for the sake of the recording, sorry guys, it's just going to be dead silence for a bit. Why do you draw a double bond? I'm not saying you're wrong, I'm just asking.
Well, I'm still ready to get out, but he's gonna make another pair over here. So for now, I just chose to have this guy also bring over
Okay.
electrons.
Okay, so what you're saying is you're processing this content in your head instead of writing it out. But you didn't write that out, you just jumped to that answer. Right?
I guess.
You did it right, so it's okay. I'm just trying to point out the intent. Yeah.
Is this right? With this? And then it says in the
Oh, you got 8, 8 and 8 is 16 plus 2, 18. Okay, yeah, I agree with you. Yeah.
And then would it be 2 electron regions?
So our electron regions would center, typically we would ask the question on the sulfur. So on this face, do I have electrons?
Mm-hmm.
Do I have electrons
Yeah.
here? Do I have electrons here?
Yes.
So how many faces is that?
Oh, 3.
That's 3.
Okay, gotcha.
Okay.
See, I'm picking it up.
We got to do a little bit careful because what you've jumped to is now saying that that is the final drawing.
Oh.
Okay.
Is that
Which
the final
maybe it
drawing?
is. I don't know.
I thought
Are
it
you?
was. Well, what else would you do? Right?
Is there another step? Yes.
Yes, there is.
It's step 6. It's the painful step.
Fixings.
You have a computer. Why don't you have the computer up? Oh, yeah. Okay. Never mind. Go ahead. I was going to be like, you could have it up to the slide that has the directions.
Oh.
What was step 6? Well, you also now have it right here. What does octet mean? How many electrons around that? Sorry. So you've got 8 and 8, which is 16 electrons. You need 18. So could that be a representation for a different molecule? Yes, but it's not the representation for this molecule. Where do you have to put that last pair of electrons? Okay, so do you really want to place it where you already have electrons, though?
No, so I can,
Yeah,
okay,
so you can put it up there.
I can remove one from one
Yes.
and between three
And then, yep, but you would need to make sure your lone pair showed up all the way down. Yep,
yes, and
lovely.
here,
Yep,
and I remove both.
yep.
Okay, great. This one.
That is set up correct. So now what you would have to do is move into step 6.
Does this work?
Yep. So steps 2 through 5. Can I get rid of that cursor? Yeah, nice. Okay, steps 2 through 5. We've got our sulfur, and just because I don't think I saw anybody do this, we'll go ahead and be obnoxious and show it in a slightly different formation. There's our box, and I don't know that anybody showed boxes, but I wasn't watching that carefully. I'm going to draw the oxygen there, and I'm going to draw the other oxygen up there. Okay? Okay, and if we're like, oh no, I do it on the sides, does that matter? No. Once you've drawn your orientation, you now need to maintain that orientation all the way through for sake of dealing with the all-important step 6. So the location ultimately doesn't matter right now. Okay? I want the sulfur in the middle because it's the least electronegative. Our oxygen is more electronegative than the sulfur. Okay? So now we'd move on to placing our electrons. Where do we start placing our electrons? I want to place them on the oxygens. Why on the oxygens? Those are more electronegative. So I'll place pair, and I'll start placing the pair. Again, it's another square on the oxygen officially. Okay, but I'm going to start placing it on that bottom side towards the sulfur because I know I need a connection there. Okay, again, not a big deal because when you place your 8 electrons, you're going to have to fill all those out anyway. Okay, same deal for the bottom oxygen. Okay, and what I saw a couple people do is now move on. Whoa! I feel like I was just the Flynn science guy in this stupid video. Damn it. How many electrons was I supposed to place? 18. How many have I placed? 16. I'm too short. Okay, that's the first time I ever said that. Okay. I need to place 2 more electrons. I can't place them on the oxygens, which means I have to place them on the sulfur. Okay, where should I place them, left or right? Okay, ooh, cool, we got lots of different answers out of that. Does it matter? No. Okay, so all you have to do is make sure that they're placed. Okay, just like the oxygens, as long as they're placed, you're okay. You don't want to split them up, okay, because that's a way more advanced thing that you don't want to stress about. Always keep them in pairs. Okay, at this point, I now have my 18 electrons. My step 5 would be wherever I have a pair of electrons between atoms, I can turn into a bond. Okay, I'm going to draw it over the top because I'm going to redraw it for step 6 in a second. Okay, and I've got a bond there and a bond there. So if I tried to erase, it's going to screw that up. So if we clean that up a little bit, we've got sulfur, bond, bond. There's my oxygen, my oxygen. Those dots look really tiny on my screen. Are they at least visible for you?
Yeah.
Okay. Okay. And that's what came out of step 5. Step 6, before I continue on to any other steps, is I need to go through and consider, okay, what? I need to consider octets. So every single atom should have achieved their octet. Okay, we don't have any hydrogens here, which means every atom should have 8 electrons around it. If we go through and look at the oxygens, yes, they have 8. What about the sulfur? It only has 6 electrons around it, which means I need to move a pair of electrons from one of the oxygens towards the sulfur. I don't want to move it from the oxygen to the sulfur, because then what happens to the oxygen? It would lose its octet, and that doesn't work out. So I need to move it to a space where both the sulfur and the oxygen have access. Okay? So I'm going to move that pair of electrons to there. Well, dang, now what do I have? I have a pair of electrons between atoms, and I can now call that a line. How is that 2 lines different from the 1 line I have above it? It's now a double bond. Why do we have double bonds? Not because I just felt like drawing them. It's because I'm trying to satisfy an octet. Double bonds come into existence for a reason. Pay attention to that reason. Okay? Did I have to take the electrons from the bottom oxygen? No. I could have taken them from the top oxygen. What would have changed about my drawing? My drawing should look like the double bond up top. And now we run into this weird kind of gray area question that we'll go ahead and ask. Are those different? Okay. And this one gets gross because couldn't you just turn it? You did the whole Mike and bendy mic. Okay. There's still Mike. When we're dealing with resonance, your structure is now pinned. Okay. You cannot move the structure around. What we're concerned about is where the electrons can move within it. Okay. And so that means these 2 structures are now unique from each other as far as resonance is concerned, because I have a double bond with the top oxygen versus the bottom oxygen. This suggests for this particular compound, I have 2 resonance structures. Okay, so if I was asked to draw the Lewis structure for sulfur dioxide, I should be drawing both of these. Okay, there were lots of hands that came up.
When it comes to resonance, that would be the only 2 resonance structures. You don't need to the left and right. Like orientation doesn't matter. It's about the bond.
So it's about the bonds. So that again comes back to once you have picked your orientation, you're locked in that orientation. Left, right doesn't matter anymore.
Kind of to piggyback off her question. So if it wasn't the double bond and it was just the 2 unbonded electrons on the sulfur, it wouldn't be resonance, and we wouldn't have to show that those unbonded electrons can go on the different sides of sulfur. Does that make sense? It's not about showing where those extra electrons can be, it's just the bonds. Like, would you have resonance if you didn't have the double bond? Because you have to show where the different electrons can go on the sulfur.
I need to twist my sulfur now. I'm not quite sure how to answer your question. Come on, give me an oxygen.
So if you had just the green image, and let's say,
But that has double bonds. So if we're here,
yeah, okay. In that instance, would you have to show resonance by showing that the unbonded electrons on sulfur can go on different faces of the sulfur, or no?
which does apply back up to that. So could we go through and say, we'll actually draw it up here in black. I'm quickly drawing those dots. Is this a new resonance structure?
Yes, thank you. That's my question.
No. Okay, that goes back to the orientation. You've changed the orientation of where you're placing those electrons.
So it's just the bonds.
Okay, we're really focused on how the bonds can shift around.
So, I just want to make sure I have the concept clear. So, if I did, like on your bottom example, if I drew it left to right instead of up and down, then I would only need 2. So, if I had the double bond on the left first and the single bond on the right, then I'd have to draw again with the double bond on the opposite side, but not
Yeah.
the up and down.
Yep, you don't need the up and down. That goes back to you're now changing the orientation of your structure.
And it doesn't, so it's most important about showing both structures of the double bond, not the 2 remaining electrons on the sulfur. Is that correct?
Well, if you get rid of that pair of electrons on the sulfur, what becomes the issue?
No, I mean, like, because I drew them on the top of this one, so then I draw them on the top on the example on the right. I don't need to keep redrawing it with now the 2 electrons on the bottom of the sulfur. Is what I'm asking. Does that make sense?
No.
Okay, so.
Oh, wait, because if you're saying it's the same question,
Yeah. Yeah.
so are you saying, we go back to this one. Is this another resonance structure?
Yes, yes.
No.
Okay.
Okay, because at that point, what you've done is you've unpinned your electrons. Okay, so your electrons are pinned in that initial assessment, and now where you're changing those is you're changing more than one thing.
Okay.
Ish? Feeling okay?
Sorry, another quick question.
Go for it.
So if the question was to draw the Lewis structure of SO2 with the formal charge of like -2, would we then be responsible for drawing 20 electrons instead of 18? Because I don't understand the charge.
We'll come back to that in a second. Let's finish this one out first. Okay? Because what you're now doing is changing the entire question. So we've got our two resonance structures. Would we now be done?
No.
Why not?
Charge.
Okay. Was the molecule charged?
No.
So?
Yes,
Yeah, we are done. Okay. So you would just leave it at that. Okay. If you continue to watch the formal charge stuff, this is why I would recommend you don't do that and why I have the alert on it, because then you start to see, oh, what I can do. And some people are like, oh, it's not that bad. Some people have a hard enough time with this. I don't want to make it worse by adding a whole nother step. Okay. So I'm trying to avoid that conversation and leave that for 151 or organic chemistry, unfortunately. Okay. Next thing that I will also go through and add, if resonance is something that you're like, this is mind bending, I'm not sure I can figure out how I could possibly navigate this. You are not alone. Okay? Organic chemists have to use resonance all the time. This is the introduction to set you up for this with more straightforward examples. Let's go with that. Okay? When you move up into OChem, you now continue even more resonance. Okay. Well, do they get it then? No. Okay. And unfortunately, most students continue to practice and learn how to manipulate and work with resonance all the way through an entire year of organic chemistry. And theoretically, by the end of that, the hope would be that they're adept at dealing with resonance. Okay. So you are probably not going to perfect this. That's okay. Don't stress about it. I want you to be thinking about these pieces and the process behind how we build it. Okay, if you're one of those students that needs to continue on for more chemistry and you need to see OChem, this might be a topic you want to press on a little bit more to help make sure you're a little bit more on solid ground when you move to OChem. But if you don't need OChem, resonance could be one of those things of, well, damn, I missed that structure. Okay, how many points is that going to be? At most 1. Is that going to break your grade? No, so don't stress. Okay. The next thing that we could go through and do with this is, again, this is just the Lewis structure. It doesn't have the shape. So how do we deal with the shape? We go through and we evaluate our center atom. Well, which structure should we look at for the center atom? It doesn't matter because it's going to be the exact same answer. Okay, that's one of the things that's actually kind of neat about resonance. Okay, so we could go through, I think my red one looks the nicest. And I'm going to put a box around my sulfur, which is more of a rectangle, but it's close enough. And I would go to each of the faces of that sulfur and ask, are there electrons? So if I look to the left face, do I have electrons? Do I have electrons to the bottom face? To the right face? No, okay. How about the top face? How many regions do I have electrons? 3. But that top one had more electrons. I don't care. Does it have electrons is all we're asking. Okay, so that has 3 regions of electrons, and if we have 3 regions of electrons, that means what shape do we get? Okay, tri for 3, right? Okay, and then if you tried to manipulate this, this would actually work okay with the marshmallows. What you'll find is that they're going to arrange themselves in a plane, okay, a flat plane. That's why we call it trigonal planar. Okay, and to it being trigonal versus trigonal or any of those other terms, I have no clue. Okay, you're not taking it as an oral test, so don't stress about it. And even then, if you called it something goofy, as long as I figured out what you were trying to say, I would accept.
As far as we're concerned for fundamental, is the region ever going to exceed 4, the electron region?
For the fundamental, it will not exceed 4. Okay, for anything I give you, remember you could go out and find questions. And if you find questions, it could exceed 4. Okay? The next part to evaluate, once we've looked at our electron regions, is we would then push it a step further and look at our bonding regions. So when we looked at those 3 faces, we take a look at the top. Are those bonding regions? Yeah. So that's one bonding region. If I look at the bottom, one bonding region. So I've got 2 bonding regions. To the left? No. So I've got 2 bonding, 1 non-bonding. What shape does that correspond to? Okay. It's definitely drawn like a line. But remember, all the electrons are trying to get far away from each other as possible. You're like, oh, the 2 bonds are going to get away as far away from each other as possible. But also remember, what else is floating up there? That non-bonding pair of electrons, which is also equally trying to get far away from everything else, which means it's going to bend. Okay, and the shape that we would get is bent. Okay, so this is where we have to be careful when we look to molecular shape, is that the molecular shape can be way different from our drawing, because our drawing is Lewis structure, not a proper 3-dimensional representation. Once you've drawn the Lewis structure, you could go back and be like, well, damn, I drew it straight. It's not really straight. Let me be a better artist and actually address the fact that it should be bent. Okay, absolutely cool. That's awesome. That's more than I'm asking you to do. Kinda, sorta? Questions?
So I'm trying to think of like an example where, because I know one of them was an example of a linear, so that would mean, never mind, I think I just answered it in my head.
Okay, that works. And what I would recommend you do is play around with a bunch of different examples. Try to come up with things that would represent that. The tutoring center, that same worksheet that has what we just went through with all these boxes and the rules, the flip side of it has a table that admittedly shows more than 4 electron domains, but in each of their little table columns, they provide example structures or example formulas. So you could use those formulas to see how you could get a linear shape versus a bent shape versus, if you really wanted to, the trigonal bipyramidal shape. Okay, so all of those things are possible. The worksheet can help guide you with those examples.
But if we look at the oxygen as a freedom, we have 4 regions of electron, and so after we remove, oh yeah, but maybe because I have 1 and 4, it's maybe the same. 1 and 2.
Okay, so I think what you're doing, maybe, is that you're now looking at this and saying, but isn't this linear? When we're asking the shape, it's all very specifically referring to one particular atom. Which particular atom? The central atom. So you started to talk about oxygen. I don't care about oxygen, I care about the sulfur. Okay? You'll always look at the central atom. Okay? For giggles, because you know it's fun, right? Let's not look at the central atom. Let's look at the oxygen. What is the shape around the oxygen? Well, if we look at the oxygen, we've got 4 groups of electrons around it, right? Okay, do you need to see the square or you got it? I think I heard foreign languages that confuse me, so I'm going to draw a yellow square. Okay, so if we look at the yellow square, we've got 4 regions of electrons, so that would be a tetrahedral electron geometry. What would its molecular geometry be? Well, I see 3 regions of non-bonding and 1 region of bonding. What does that correlate to? That's now the linear shape, which doubles back to your system. So if I want to look at the shape for the oxygen, I would call that a linear shape. Okay? Should I? You can do whatever the hell you want. But the question we're asking is always going to be focused in on that center atom. Kinda, sorta?
Yeah.
Okay. We're going to do the next example real fast. Because I'm going to say that wasn't particularly fast. Okay, we're going to make a subtle change to this because it was requested. Okay, the request was that what happens if this wasn't sulfur dioxide, but it was SO2 minus 2? Well, is that going to change things? What is that going to change? Yeah, in our initial count, In step 1, we still have the sulfur, we still have the 2 oxygen, so we're going to get the 18, but now I have a charge to account for. That charge means I'm going to have to either add or subtract electrons depending on what that charge is. If I became -2, what happened? I had to have gained 2 electrons. So mathematically, what do I need to do? I have to add 2, and I'm now looking at 20 total electrons within the system. Okay? And if we pulled this one all the way out, you'll notice that I've already skipped steps. We would get this, right? I skipped steps, but I wasn't paying attention to the steps I skipped. Each oxygen has 8, which gets me 16, and then I've got 18 with the lone pair above and 20 with the lone pair below, which then means I have a whopping 20 electrons. Since I've got 20 electrons, I've totaled all my electrons, and I can now move into the next step. What was the next step? We could change pairs of electrons into lines. I did that. Next step. Move non-bonding electrons into bonds to satisfy octets. Does the oxygen have an octet?
Yes.
Does the other oxygen?
Yes.
Does the sulfur?
Yes.
Do I need to move any electrons? Nope, which means? We're so close to being done. But the very last step is we have to acknowledge that I have that charge. To do that, and now I'm done. Okay. How important is that step? So unimportant that when I ask it on a test, I always universally, let me tell you, forget. And I have to regrade everybody's flipping exam because somebody remembers it. And as soon as I see it, I go, oh, crap, I got to go back and grade everybody else's again to make sure I account for that. I mean, it's fair. It's consistent.
Real quick, so this was, I think, the question I answered in my head because the sulfur has the 2 pairs of electrons on top. That would be a linear configuration. Is that correct?
Cool. How do we determine the shape? Where do we start?
The middle atom.
Middle atom. And what are we looking for on that middle atom? Faces of the square. I don't see a square, so let's draw a square. I've got my square. How many faces have electrons? 4, which would mean the shape would be tetrahedral. It's a little bit vague. We should actually call that the electron shape, being tetrahedral. Okay. To get to the molecular shape, I would now evaluate whether I have bonding and non-bonding. And when I go through and evaluate that, I've got 2 bonding and 2 non-bonding. What shape does that produce? And you're like, well, I don't know. I didn't do any of this. Oh, I get it. Okay. So let's try it differently. Tetrahedral, right? What did a tetrahedron look like? There it is. We'll summon some devils. Okay. So let's go ahead and fix this. This is our basic shape. All the electron groups are going to repel away from each other. Okay. Except my wrist now disappears because that is non-bonding pair of electrons. My thumb now disappears because also a non-bonding pair of electrons. What shape do I have left? Okay, bunny ears. This is why we have to follow standard language. Okay, that's bent. Okay, so that's still not going to come out as linear. Okay, does our drawing look linear? Hell yes. That's why you don't use the drawing to figure out to determine the shape. You use the drawing to determine the electron regions, and then you use the electron regions to determine the shape. Hit me.
So when there's a pair of electrons, even if they're not bonded, it almost still behaves like the bond.
Yes.
Kind of pushing everything.
It absolutely still behaves like the bond. Yep.
Okay, I see.
Clarify things from the lecture video. So the electron pair geometry is going to be that linear trigonal, and then the molecular shape, if there's no non-binding, it stays
The same.
original. But if it changes, would you just accept the answer bent, or is it a tetrahedral bent?
So that has multiple layers to it. So let's go through and say if this was a test question, what is the shape of this molecule? Is that show your work or is that multiple choice? That's going to be multiple choice. So if it's going to be multiple choice, you're going to have a list of answers, and you could very well have tetrahedral and bent on this. When should you say it was bent? If the question asks what is the molecular geometry, when should you say it was tetrahedral? What is the electron geometry? So that first word becomes real critical in differentiating which category you're trying to pin it into. Does that make sense?
You said electron versus molecular.
Electron versus molecular. Yeah. And when in doubt, raise your hand and be like, I don't know which one you're asking for. I may not be able to help, but I might go through and be like, it says with that first word, that word is what you should be using to classify this.
Is it always going to be bent if there's electrons that are in a bond and also unbonded? Or does it matter
Nope.
how many?
It matters how many. Okay.
Solve that trick.
Yep. And I did not open up that lecture, so I don't have that handy. But what I would do is pull up that lecture and see that chart, because that chart is going to set you up with it. Okay. Like I said, again, you can play around with marshmallows and toothpicks and try and figure out those shapes. That's going to give you the rough idea of what they're looking like, but you have to be able to identify the name. Other questions on that? I'm going to delete it all. Maybe I'm going to delete it all. Give me my cursor back. And then let's see. Cool. N2 wasn't done, right? No? What do you think? N2 or BR03? N2? Okay, do N2. We don't have a whole lot of time left, but I think we got enough time that I can at least rip through these two. If you've got questions, again, raise your hand. Okay, I'm going to talk while you're working for a little bit. In the walk around, I'm seeing people really be slow to actually activating with these kind of questions. We're asking a question in class. You should actively be engaged in trying to draw it out. Okay, if you are not actively being engaged in drawing it out, why did you come to class? You're like, well, because you told me to. No, I didn't. I said I'm not going to take attendance. So if you're not going to actively engage with the content, then maybe you shouldn't come to class. Okay? That is a double-edged sword, because you're losing the opportunity to practice. Okay? But if we look at our class, there are people that have chosen to not come to class. That is okay. Right? And if people are watching it at home, that is okay. Just realize the point of being here is to engage in the content so that you're actually starting to learn, not just listen passively. I regret doing this.
I have no idea what is telling me I'm doing it wrong.
What was the formula?
N2.
What does the 2 mean?
But there's two. Oh, so
How many did you draw?
there's two.
Yeah, perfect. That's exactly what I want to see.
No, because then that would be 16.
So when you place electrons, how do you place electrons?
Around
Around what?
the faces. Right?
Of what?
The element.
Which element? Cool, the most electronegative. How many electrons do you place? 2 until what?
Until you hit the 8, right?
Till you hit the 8. Do either of your atoms have 8? So did you decide to do something else? Yeah. Okay, and by doing something else, what happened? You set yourself up in a weird spot where it now becomes hard to actually figure out what happens. You don't have to apologize. This is the point. You should screw it up right now.
Is this possible?
It is.
Okay.
That is the answer. Okay. Though, if I'm going to track your work, I don't like your work.
Okay.
How did you get to this?
I tried like 5 different ways. So I had the first one where I put them around the first one first, and then just bridged one time, and I went. And while I was working it out and just going like, well, this doesn't equal 10. Because I knew
Well,
that the two together would have 10 electrons, and so I had to
cool.
have,
Did you place all your electrons yet?
on this one I did. So I started to. And so I started with just going 8 here first.
Yeah.
And then I tried.
No, just finish that one.
Okay.
You need 10.
1, 2, 3, 4, 5, 6, 7, 8. So then 9, 10. But then this doesn't have an octet.
Cool.
So
How do you fix it?
I have to pull 2 from here, bridge it over.
Yes.
So then I can go, that still doesn't work. And I can pull 2 from here.
Yes.
Over. I see.
So the work that you showed me is I didn't like this.
Okay.
You didn't finish it, and then you went to this. And you're like, well, fuck it, I'm just going to start drawing lines and hope it works. No, that's a bad process. I don't like that process. Okay, so, and this one does trip a lot of people up for a couple reasons. So I do want to call out one of the most common mistakes is people will draw this one out and they'll just draw N, and they'll be like, I can't figure it out. Deep breath, slow down. Remember, lower right-hand corner is the amount that element shows up. Okay, so exams will mess with your brain. So if you're doing it right now, the exam is going to make it that much worse. So practice to make sure that the exam doesn't happen. Because H2O, exam time, guess what the structure becomes? Or OOH. You're like, what? How'd they do that? They put the 2 and they said the 2 meant the oxygen. Lower right-hand corner. The 2 is next to the hydrogen. Pay attention to where your numbers are. It's very, very critical for interpretation. Okay? So yeah, all those were wrong waters. Yeah. Okay, so let's get our nitrogen. So now the next part, I want to place electrons. Where do I want to place electrons? Around the nitrogen. Which nitrogen? Cool, doesn't matter. Pick one. Okay, I'm going to start by placing them in between because I know I need a connection there. Okay, for me, whatever reason, it's not whatever reason, I read left to right, so I'm going to start placing them around the nitrogen over here. Okay, one of the common things I'll see is people stop with that. How many electrons was that? That was 5. You're like, why would you stop with 5? Why do you think someone stopped with 5? Nitrogen brings in 5 valence electrons. You're doing the stupid Lego shit. Stop it. Okay? It doesn't have 5 electrons. It needs 8. Draw 8. Okay? Now that I've got 8, but I need to draw 10. So, I need another pair of electrons. The only place it can go is on the nitrogen. Okay? I think I heard a yeah, but, so that's fun. I like that. Of course, my eraser, totally toasted that. So I could draw a line in between, okay? And the but is probably that the nitrogen doesn't satisfy its octet, right? So what do? This is kind of the concept of resonance, except it's not resonance that we have to worry about because there's not multiple ways to go through and do this. There's only one way to do it, but you do need to satisfy octets. You're going to do that by removing a pair of electrons from that nitrogen and placing it in between. I now have a pair of electrons between atoms, which means line, which means double bond. How many electrons on my right nitrogen? Not enough. So I do it again. Now that I have a pair of electrons between atoms, I turn it into a line. And wow, what do I have? Triple bond. The triple bond came into existence to satisfy octets, not because I felt like I needed a triple bond. That's not how it works. It comes in because of how we place our electrons. That is very hard to process because of how you're looking at answers online. And I get it, okay? But follow the process, it locks you in pretty well. If we were to go through and do the BR03, I know we're done, so you can definitely pack, right? We are done? I don't have a clock. Okay. Okay, also I'll just talk it out. Bromine is 7, oxygen is 6. There's 3 of them. If I did that math right, that's 18. It's a -1 charge. So what I would write is charge to become negative, I needed to add an electron, which means I have 19 and 7. Oh, shit. Thank you. 26. Bromine, oxygen, oxygen, oxygen. 2, 4, 6. I didn't start placing electrons in the right spot that time. 2, 4, 6, 8. 2, 4, 6, 8, which gets me my 24, which means I need 2 more on the bromine, which then means, oh, balls. Whoops. Gah. That's what happens when you try and go too fast. Bromine, oxygen, 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 oxygen. All the dots, all the dots. Oxygen, 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 oxygen. Okay. Okay. I did just lose one person, which is kind of unfortunate. If you go online and you check to take up the Lewis structure for BR03, is this what you get? No. The internet will give you a different answer. Why? They know more rules. You don't know those rules. So be real careful looking up Lewis structures online, okay, for why you would change things around. Okay, this was darn close to the end of the last part that I forgot. I need my brackets with the minus sign. Okay? If you got questions, feel free to stick around and ask. I'm going to stop the recording, but then I'll come back. Yeah.